Welcome to a new problem solving session, and this is a simple yet common problem but can be useful. And as the heading can read, is it a correct statement? And what is the statement exactly? If the point of application of force does not move, then no work is being done by the force. Is it correct or not? I'm going to check it in this problem. And here is the problem itself. As you can see at the screen, at the end of a board of mass m, there is a small block of mass m1. The board can slide without friction along the horizontal surface on a table. There is a problem with my mind. My mind always shifts to the future statement or future thought. So I usually spell or write or speak something else from the next statement. This is inherent. So I'm sorry about it. The coefficient of sliding friction of the block on the surface of the board is mu. And that means block and the board contact is rough. The board is given a horizontal velocity v0. The board is given a horizontal velocity v0 by push. At what length of the board L can it slip out from under the block? That means कि बोर्ड को स्लिप करना है ब्लॉक के अंदर से, इसके लिए कंडीशन मांग रहा. Though this problem can be solved in many ways, but I prefer if I had a diagram of all those things, because and I have one. This is the diagram, though this diagram explains a lot, but I would like to start the problem from the very beginning. There is a friction between block and the board. This is the block and this is the board. And the friction between the board and the block plays a dual role. The friction acting on the board slows down its motion because it has been given an initial velocity, so friction should act on the board in this direction, and it will act in this direction on the block. Friction is acting on the block towards right and on the board towards left. So the friction force acting on the board slows down its motion, and the friction force acting on the block accelerates it. It is accelerating. It seems weird, but it is accelerating friction. And guess this friction is sliding friction, kinetic friction. And this will continue until either the board slips out from under the block or their velocities become equal and they slide together as a single body, remaining motionless relative to each other. So there are two conditions. Let us assume that the velocities of the board and the block are equal, and the block having traveled a distance s along the board. This picture I am referring, this displacement I am referring, that I have assumed a condition in which velocities of the board and the block are equal. That means block has gone motionless with respect to the board. The velocity of the block with respect to board is 0, and this has been observed after the block traveled a distance s with respect to the board and has not yet reached its opposite end, and since there is no friction between the board and the table surface, this one, so the momentum of the board block system is conserved. If I consider them both as a system, that means board plus block, friction between them is actually the internal force, and external forces are missing in horizontal direction on this board block system. So the total momentum of the board block system along the horizontal is conserved during this motion, and as a result, if the velocities of block and the board are equal, and I assumed it as it being v at this moment because its initial velocity was v0, so the equation for momentum conservation can be simply written as mv0. At the start of the motion, board was given the velocity v0, and at this moment the total momentum is m plus m1 multiplied by v. So you can find v from here, and this will come like this: v equals m by m plus 1 v0. Now let us calculate the change in the mechanical energy of the system in the case under consideration. It is obvious that the work of the friction force acting on the board is negative, because the force of kinetic friction is acting on the board in a direction opposite to its velocity. So I guess it is doing negative work, and I have given a whole module of displacements of board and block with respect to the ground or with respect to the table beneath them, and in this reference frame, S1 and S2 are the displacement of block. I think board is the displacement. The displacement of board is S1, and the displacement of block is S2, and this is the displacement of board. S is the displacement of board with respect to the block, and you can see here in this picture alone that S is equal to S1 minus S2. But I was talking about change in mechanical energy, and there is no change in gravitational potential energy of the system. So I would like to write work energy theorem. I would like to write the work energy theorem for the whole system, and there is nothing wrong in it, so that I can write something like work done by friction force on the board as minus mu mg s1, and for the block I can simply write it mu mg s2, and this is the work done by friction forces acting on board and block. And then I would like to write the change in kinetic energy. So final kinetic energy of the system, or since both have same velocity, so it will become half mv square plus half m1v square, and initial kinetic energy of the board was half mv naught square. I have to write only the change in potential energy. So this is it, work energy theorem. I can write one more. Oh, that is all right. Or I can write it like this: that m plus m1 square by 2 minus mv naught square by 2, that is equal to minus mu mg s1. This is the same statement, plus mu mg s2, and like this. This is one of the equation 2, suppose that, because there is equation 1, and this is a kinematic relation between visible kinematic relation between displacements of board and the block. And you can see here I can easily put s1 minus s2 here, because mu mg is common in both, so I can put here s1 minus s2 equals s, and after substituting s equals s1 minus s2 in both equation 2, basically in equation 2, you can get simply like s equals half m by m1 plus m2 v naught square by mu g. This is, but I would like to discuss the problem more, because there is something else I need. However, I have used the equation number 1 also to find this equation. I would like to give it equation number 3 and number, and ये तीसरा equation हो गया. But if the value of s given by this relation turns out to be less than the length of the board, then everything will be exactly as described in this solution. But if it turns out that s is greater than L, then the speeds of the board and the block will not have time to equalize while the block moves along the board and having reached its opposite end, and the block will fall off the ground. Thus the answer to the problem is not valid in this case. So this answer is correct under one circumstances. If L is less than S, then I could write the answer. This answer is correct. I mean to say, ये आंसर तभी सही होगा जब ये कंडीशन फॉलो होगा कि this length L is less than S. And of course this problem can be solved using the laws of motion, which would be more cumbersome though. But let's pay attention to two essential points. First, we sometimes say simply, or sometimes the statements like this is mentioned before us or written somewhere, that work done against the friction force is done at the expense of the energy loss of the system. But as can be seen from the example of this problem, the work of different friction forces can have different signs plus or minus. Therefore, using the method of reasoning in the quotation I was talking about can lead to a fundamental error. What I am trying to tell, let's summarize in one sentence. What I am telling you, when calculating the work of the friction force, it is necessary to consider the displacement of the body on which it acts, not the displacement of the point of application of the force. फ्रिक्शन फोर्स का वर्क डन निकालने में हमेशा हम लोगों को वो जो पुराने ज़माने की लोनी के ज़माने वाली जो स्टेटमेंट है उससे बचना चाहिए. We need to consider the displacement of the body on which it acts, not the displacement of the point of application of the force. Because let's take an example. Here is the figure I have drawn, and this simple example makes something clear. Suppose there is a board moving along a smooth table, experiences friction only at one point, that is point A. Where there the contact is rough. And when the board moves, the point of application of the friction does not move in the laboratory frame of reference. Lab, with respect to ground, the point of application of the friction force does not move. But nevertheless, the friction force does negative work, reducing the kinetic energy of the board. And I made my point. But there is also a point that friction force, people will often seem to be confident enough that friction force comes, especially when the force of kinetic friction comes into our minds. We usually think it does negative work. But in this case, it accelerated and decelerated the bodies. It has decelerated the board and accelerated the mass M1. So it can, even the kinetic friction can do positive and negative works. So keep in mind and don't worry. And now you can solve, and this is a solution, and you can solve anything you want. Thank you very much for watching. I am ending the solution.